Hey, good afternoon, ladies and gentlemen. It's 3:31 of the p.m. and it's time to do some math. So let's get to it. So this first problem you're here with tonight, in terms of your homework, is to confirm that 4-6, or actually answer if 4-6 is a solution to this system. So remember, a system at its core, a system is a set of equations that have to be solved together. So a system means the answer has to solve both. Okay, that is what this little bracket implies, that these equations are somehow related, they work together for some reason. So the 4, comma 6, which of course is going to be the x comma y, has to solve not just equation 1 but equation 2, which tells us exactly how we're going to check it. So we're going to look at these two equations separately, but we're going to check to make sure 4-6 works in both. So over here we have the x plus 2, over here we have the 10 minus x, and let's just check to see if 4 comma 6 solves both these equations. Let's check this one over here first. Well, again, this is the x, this is the y, so we're going to do a substitution. Instead of the y, we'll put a 6. Instead of the x, we'll put that 4. And we'll just check to see that this equation really is an equation. So 6 on this side has to be equal to 4 plus 2 on the right. Well, of course, 4 plus 2 is 6. This one checks out, hence a happy face. Now let's check it over here on the right. Instead of the y, we'll put that 6. We're doing substitution again. 10 minus, and instead of the x, we'll put a 4. Now we're checking the equation, both sides, see if they're the same. 6 is equal to 10 minus 4. Well, that's 6 again. And of course, that's going to work as well. Now, since it worked on both equation 1 and equation 2, we can definitely say, yes, this is a solution. So before we go to the next one, let's review the steps. So if we're dealing with a system, hence the bracket, it's got to solve both equation 1 and equation 2. It, of course, being this potential point, x comma y, that we're supposing is a solution. Now, you might want to start thinking about, to kind of get a head start on the next couple days, is why we're trying to have you to write it like this. I know we said shorthand in class, but it has to be something else. That looks an awful lot like a coordinate point, doesn't it? Hint, hint. Moving on to question 2, same kind of question. We're going to deal with a question whether or not it's going to be a solution. So let's break this up. We're looking at 6 comma 6. It's going to be pretty easy because it's both an x and a y. We have equation 1 on the left. Let's put it in purple. I like purple. X plus y is 12. And then we have equation on the right. 2x is equal to 10. So it's got to work in both equation on the left, equation on the right. So let's get to work. So we'll put the 6 in for the x. We'll also put the 6 in for the y and check to see if that adds up to 12. Now, I know some of you guys are saying, oh, Mr. Collins, I could do that in my head. Well, that's fine. Do it in your head, but you still have to show us at least some of the work. So 12 equals 12. That works. Happy face. On the right, I don't know if we're going to have such a happy ending here. We're going to put the 6 in for the x. Notice there's no place to put in that y. So we're just checking to see if 2 times 6 is the same as 10. Well, of course it's not, it's 12. So that equality is untrue, so the answer to this is no. So again, we're doing a substitution, checking to see if it works in both equations. Since it didn't work on the bottom equation, the equation on the right, it is not a solution to the system because it has to solve both. Let's go round 3. So we're going to check is 0 comma 8 a solution. Again, let's remind ourselves that's the x and that's the y. And that we have to check both equations. 2x is equal to 16. And x minus y, whoops, is equal to 8. So let's do some substitution and checking. So 2 times the x value, which will be a 0, is equal to 16. Well, 0 is not the same as 16. This is a false equation. I only have to check the one on the right. I don't care about the one on the right. It didn't work with the one on the left. Therefore, this is a big fat no. If it doesn't solve both, it's not a solution to the system. So checking the one on the right is actually unneeded. Okay? Let's move on to this one. Claudia. Let's talk about Claudia. Claudia's trying to get the word out about a voter registration rally next week. She wants to use all of her free 90 minutes to make phone calls and send emails. She needs to get rollover. And then she needs to reach a total of 26 people. If it takes 5 minutes for her to make a phone call and 3 minutes for her to personalize an email, how many phone calls should she make and how many emails should she send? So the first step is, and this is a big one, we're going to have to start getting used to this really, really quickly, is defining the variables to use. So let's use the language we use in class. So let, okay, and let. I don't know what variables you are choosing to use, but I love x and y. That's how I am, so I'm going to choose x and y to be our two variables. So it seems to me the two things I don't know in this problem are, and it's even saying it right here in this last kind of sentence, how many phone calls and how many emails. So I'm going to let x be number of phone calls, and I'm going to let y be number of emails. Right? So what is the relevant information you need to solve this problem? Well, I mean, this is such a loaded question. Here's the reason why. It's all important. Sometimes something about the situation will let you know kind of how the numbers can be. So I wouldn't say just look at the numbers and throw all the rest out. Having said that, I wouldn't say don't focus on the numbers, because those are the parts that are going to help you do the calculations. So knowing what's relevant, knowing what's not, is really an issue of knowing more about the problem itself. If we have this X being phone calls, Y being emails, what we probably have to do is look into the problem and see what information is really important to phone calls, and likewise look in the problem and see what information is really important to emails. And I'm going to try to color code it so it makes a little more sense. So when I'm reading this through, I have 90 minutes to make phone calls. Well, that's about phone calls, so I certainly would claim that this is important to phone calls. And send emails and sheets for 26 people. Like, that's important to both. So I don't know if I can really color code that. It takes her 5 minutes to make a phone call, so obviously that's about the calls, and 3 minutes to personalize emails. How many phone calls? I'm sorry. Well, let me look back and read this. So how many phone calls and how many emails sent? So she had the 3 minutes for email, 5 minutes for a phone call. The 90 minutes really applies to both. So I'm going to go back and put a little blue on this one too. So we have all this information. It's relevant. It's irrelevant. Well, again, it's really hard to kind of separate the two. So let's talk.
Mr. Collins, I think there's actually one more relevant piece of information.
Oh yeah, what's that?
I think you need to know about how many people you need to call or get a hold of.
Yeah, and I think that again applies to both. So I'm going to put this both in blue and in red.
I'd agree with that.
Because it's important to both the situations. All right, so that's the relevant information. Let's talk about the number of. Let's write one equation. Well, the equation really has to break down. One has to involve each constraint that you're actually placing. So let's go back and try to figure out the limitations we place in this problem. Well, I think Ms. Noren just actually pointed out one of them. 26 people is definitely one of the rules we have to follow, and I think 90 minutes is the other. It's pretty easy to see that because it involves both the phone calls and the emails. That's one easy way to kind of pick out those constraining pieces. So it doesn't really matter which one we do, so hey, let's just do the one about 26. So total of 26 people. Well, again, this is where we can't separate like the problem from the numbers. So 26 people, but I define phone calls and emails. So we have to kind of make a working assumption here. If I'm calling someone, I'm calling just one person. If I'm emailing, I'm hopefully emailing just one person. So if I want to make a total of 26 things, well, I'm going to count up number of phone calls, which would be the X, and the number of emails, which would be the Y, and then total them together. So if I take number of phone calls, assuming it's one per person, and one number of emails, assuming one per person, I can't talk to any more than 26 people. Okay. Ms. Nora, how do you feel about that?
I like that. I like the red and blue too.
Okay. So the other constraint is going to be this 90 minutes. Well, 90 minutes has everything to do with phone calls and emails, but it's not going to be just X and Y, because these are numbers of phone calls and emails. So if I know I need to spend a total of 90 minutes doing these things, what I really have to figure out is like how much time I'm making per call. Like, in other words, like if I make one call, how long do I spend? If I make two calls, how long do I spend? And really think deeply about how I'm calculating that. Well, it says right here it takes me 5 minutes to make a phone call. So if I made one phone call, it'd be 5 minutes. I get that by 5 times 1. If I make 2 phone calls, it's 10 minutes. I get that by 5 times 2. So if I make X phone calls, I'm going to be looking at a 5 times an X. Same reason can apply to the emails. 3 minutes to personalize an email. And I don't know what she's doing to personalize an email. Like, that's a lot of time to be emailing somebody. But anyway, we're looking at a 3 times a Y. So of course, if we're trying to make that hit the total of 90, we're going to be adding these together again. So here's an interesting question. I have these two separate equations, but why in the world can we now claim that this is a system? Hence the bracket I'm currently putting on, the Jay Leno, if you will. Well, it all has to do with the definition of a system at all. And if we kind of talked about that with problem 1. The idea of picking values for X and Y to make 26 is actually a pretty intriguing question. There are a lot of values you could pick to make 26. I mean, that could be 26 phone calls, 0 emails. It could be 0 calls, 26 emails, which is likely, by the way. And where's the text messaging? It's separate from the problem. But the point being, there's a lot of combinations that will work. So if you don't have the second thing to help constrain, to help kind of contract or hold back your combinations, you're just going to have an overwhelming number that you could actually pick. So this idea of being a system has everything to do with 2 rules you have to follow. You have to make 26 calls, but you can't spend any more than 90 minutes doing it. And that's just what systems are at their very core. Jordan, you want to add anything?
No, I think that's great. I absolutely. It's got to meet. We talked about conditions and rules today, and it has to meet both rules. That's what I think of when I see that bracket. It must agree to both rules, or it's not the solution.
And I mean, there's lots of ways to write that. The way I'd kind of encapsulate is that the x and the y have to meet both conditions. My fancy handwriting. Right? Another way to say that is that both the x and y have to solve both equations at the same time. Both x and y have to meet both constraints. Both x and y have to
meet the rules.
Be
true in both cases.
Yeah, so lots of ways to do that, lots of ways to say it, but that's the way I'm putting it. Okay, so now we have, just like we had in the front, let's do some checks. So 511 is a solution to the system. Well, it has to work in both equations at the same time. So let's have it set up like we did before. So we have 15 and 11. And these 2 equations, the x plus y equals to 26 on the left here. And the 5x plus 3y on the right. So it's a matter of substitution and... Whoa, things got crazy. 5x plus 3y equals 90. Okay, so it's a matter of substitution, checking, and see if it actually works. Let's do the work over here in the blue. So we're checking both 15 and 11 for x and y. So we have the, that is not expected. Let's try that again. Well, so we have the 15 in for the x, we have the 11 in for the y, and we're checking to see if that's 26. I know you can do this in your head, but go ahead and show us the steps to make sure you're doing it right so we know. 15 plus 11 is 26, so this one turns out to be true. Check mark. But it's not a system unless it meets both conditions, so let's check the one on the right. So we have 5 times 15, and then 3 times 11 is got to equal 90. So we have this 5 times 15. I did pause the video, by the way, to do that because I couldn't do it on the fly. So 5 times 15 is a 75. 3 times 11 is 33. Let's see if that equals 90. Well, 70 plus 30 is 100. 5 plus 3 is 8, so this would be 108. And that's not the same as 90 last time I checked. So this is not a solution. This is a sad face, maybe a little tear. And this is end up being a no, not a solution. It did not work on the second constraint, but it did work on the first. But since it didn't work on the second, we don't care about the first. Not a solution. Oh, let's check another one. I'm having fun with this one. Let's see, 6 comma 20. Let's check our equations again. X plus y equals 26. And on the right, we have the 5x plus a 3y equals the 90. I can already kind of see it, kind of look ahead that it's going to meet this one, because definitely 6 plus 20 is going to be 26. But we want to go ahead and show it. I mean, there's a difference between knowing something works and being able to explain something working, and this is precisely how you'd explain it does or does not work. Again, an idea is no good unless you can actually express it. Let's look on the right. So we have the 5, let's substitute in the 6, and then the 3, let's substitute in that 20, equals 90. Let's work this out. 5 times 6, I believe, is 30. That's going to be a 60. Oh, well, look at here.
Oh, yeah.
90 is equal to 90. That's a happy face. So that conclusion is yes. That is a solution. It works in both. That's all a solution has to do. Okay? So the question now stands, the last question is, what does it mean to find a solution to a system of equations? Well, this is actually pretty much the same question that we asked you in E. A solution is a thing that does that. So if we're looking for a solution, we're looking for the values of two variables. Or another way to say that is the unknowns. Whoa, hello. That meet both conditions.
Make it true. It has to make it true.
Okay.
In both cases.
So if you walk out of this homework knowing 2 things, you're going to be really good to go. Number 1 is, how do I actually write these equations from the situations? And I know we haven't given you much reason to actually write these equations other than we've been telling you to.
Wait till tomorrow.
But you're definitely going to see, yeah, absolutely. We're definitely going to see like how useful these equations can be in problem solving. At least we're going to do our best. And the second part is, can you check a solution, whether or not it's a solution to a system. Now, to do those 2 things, you really have to understand the definition of what it means to be a solution. But in the end, there's a couple things at play. You have the skill of being able to make the equation and being able to check the solution. And then you have the reasoning ability to tell me what a solution is and to tell me what it means to be a system at all. So those are big ideas. I hope this helped you guys. If it did, why don't you mention to a friend, get them to look on it too. I mean, we're in this together, so we might as well help each other out, right? So you guys have a great evening, and I will see you tomorrow.